Okay, so we're going to talk about section 6.1 of our book, which introduces chapter 6, which is dealing with linear systems of equations and how we solve them. And this builds on something that you've seen before in your past classes. So, what you saw before in either your algebra or algebra 2 classes, you'd have a system of equations, maybe something that looked like this: 2x plus y equals 10. And then let's just say x minus y equals 6. And you would solve these. There's different ways you could go about it. One way would be to multiply. So to take this second one, multiply it, or just add it together. Sorry, we could multiply by a value if we wanted to get rid of x. Let's say multiply by 2. And then that 2 distributes through to everything, and we can add them up, and the 2x's will cancel. Another way to do it would be to just add to solve for a value. So if we had 2x plus y equals 10 and x minus y equals 6, I could add y to the other side and get x equals 6 plus y, and then you can take that and substitute it into the first one. And we get our system of equations. So that's kind of where we've been. What we're going to focus on this chapter is how do we use something called a matrix to do this more efficiently and quickly for larger systems. That's going to be our goal. So we're going to start off with looking at some different terminology. Some of it looks scarier than it is, but we have our reference in the book, and we'll go through what these things look like. All right. So what we want to think about is, this is our key concept, our first part of this, is that we can do certain manipulations to systems of equations and not change our solution. So the first thing is we can switch our equations. So if we look at our expression here, right? So we can interchange the two equations, meaning we can swap the order. We can multiply by a non-zero number, and we can add one to the other. So if we were to look at what that looks like graphically, let's go ahead and open up a graphing system. So let me do, let's say 2x plus y. Let's just say x is 2 and y is 5, so that would be 9. And then if I do that again, x plus y, if they're going to be 2 and 5, that would be a 7. And then we can see on our graph over here that our solution 2 and 5 is where they cross. That's what we're solving with our system equation. So if I added something else where I just multiplied the blue one, let's say by 3x plus 3y equals 21, we can see that it had my same point of interval. It's the same line. That's not going to change my values. It's not going to introduce any more information. If I was to add the two equations, so the red plus the blue, that would be 3x plus 2y equals 16. And I can see, again, I get a different set, but where they cross is the same solution point. So I haven't added any values to it. So that's really all that this is saying here. Is that these are operations we can do to change things around but not lose what the solution is. And we're going to do a bunch of that with our matrix stuff. All right. So the first thing that we start off with is what's called an augmented matrix. And so really what we're going to do is, it doesn't matter what our variables are if we keep the order the same. So what we're going to do is look at the coefficient in front of our expressions, and then we're going to have what's called a augmented matrix as our solution is going to be here. So the biggest thing to pay attention to is the order. This goes x, y, z, this goes w, x, z, this goes w, x, and y. And so just like we did with synthetic division where I put in placeholders, we're going to want to drop in placeholders and talk about, well, that's a 0w plus 1x plus 1y minus 1z. And those numbers, 0, 1, 1, and 1, are going to become part of our matrix. So when we do this, and we look at our actual augmented matrix, what we're going to see is right here. So let me move that out of the way. Our value, when we add those in, is the 0, 1, 1, negative 1 is exactly this down here. And then that solution So that expression goes there. And this is an augmented matrix where we have the solutions and our expressions together. One general thing about our matrices as we look at this, we have what are called rows and columns. So this has 3 rows, and this has, in this case, it has 5 columns. And so this would be what's called a 3 by 5 matrix as we do our rows first and then our columns. All right, so as you're going through this video, what you're going to be doing for filling out is our expression, our handout. So when you get to this part, what I'm going to have you do is you should be working through this handout. We've kind of talked about these 2 pieces. The example 2, we just went through and put our example there, so you can go back to the video and put that piece in. And then for the next part, what we're going to look at is some guided practice. So for the guided practice, you need to write the augmented matrix for this system. So go ahead and pause the video at this point, and then on your handout, you're going to, the same way that we just kind of talked about, take these expressions and then write your augmented matrix. All right, go ahead and pause now. All right, so we're going back to, after you work through that guided practice problem, we're going to go back to how do we actually do these row operations. And so again, going back to what we can do, we can interchange, we can multiply, and we can add the rows together, and we're not going to introduce any different solutions to our system. So when we look at that, what we're going to try to do is get something into what's called row echelon form. Okay, and the idea with row echelon form is we're basically going to have these values here where we have one of our first variable, one of our second variable, one of our third variable, and then potentially something down here where it's a bunch of zeros. We're trying to reduce values so that we can simplify what our expressions look like. And then anything, these are general rules, anything that's just zeros goes to the bottom. We're going to have a 1 to start, and we're going to basically try to build this kind of triangular pyramid shape here with our values. So when we look at this, we're going to figure out whether this is in row echelon form. So again, what we're looking at is the values here and here, right? We have a 0 below that one. So this one has a leading 0, and the answer is yes, this is going to be in row echelon form. All right, here's another one if we look at to see if it's in row echelon form. Well, we can notice, right, that this row of zeros is up here at the top. And so this is not going to be in row echelon form. Right, again, going back to it with those values there. R1 here, we have a leading 0. Okay, we have a leading, a 1, and then our zeros are at the end. So for this one, this is going to be in row echelon form. All right, so we can get things from what we started with our augmented matrix into what's called row echelon form, and we can do that by using, again, these key concepts of row operations. All right, so if we wanted to look at this, so what we're trying to do is to take an expression, and we're going to take our augmented matrix. So we take our system of equations, which is up here. We write an augmented matrix, and then basically we're trying to transform things to drop them out. So if I look at my first row here, 1, -1, 1, and I see the row below it, -1, 2, -1, the way that this has been annotated is if we think about this as R1, R2, R3, if I add the first 2 rows together, the 1 and the -1 are going to go away, and they're going to cancel. And then -1 plus 2 is -1 and 2 is going to go to -1. Sorry, it's going to go to 1, and -1 and 1 is going to go to 0, and I rewrite that expression there, and then the 3 and 2 add up. So if we take that idea of basically adding rows or multiples of rows to each other, we can start to put things into reduced row echelon form, and that's what's just called our Gauss-Jordan elimination. All right, so we get to this point, we can see R1 plus R2 gets us here. R3, which is 2, -3, 3, minus 2 times R1, okay, because we want this 1 to become a 2 so we can cancel it out, drops out that piece there. And then we take 3 times R2. That's a 3 times a 1.